Hi everybody, today I want to consider this very simple AC circuit. So I have a time varying voltage here, which we'll define in a minute, one resistor and one capacitor. And I'll show you an example of, why we use capacitors in circuits. They can use for a lot of different things. Capacitors can be used to store energy that you can then use later on. Capacitors can be used to produce constant electric fields if they're parallel plates. Capacitors can also be used to filter signals and AC signals. So that's what we're going to look at today. So here's the basic circuits, one single loop. And what we're going to be interested in is applying Kirchhoff's loop rule and looking how we can calculate the voltage across that capacitor for different values of the frequency and see what happens. So we're going to start off by doing something qualitative just to try to get a feel of what we think is going to happen. And then we'll do some math. We'll have to look at phasors. We'll have to look at the reactance of the capacitor. We'll have to calculate the current as a function of time. And then at the end, we're going to get the voltage, and I'll show you how to do everything. Okay, so again, the rule is if you like the video, give it a thumbs up. If you like what I do on the channel, consider subscribing. If you have any questions, leave a message down below. All right, I want to first consider the DC case here. Let's recall what happens. So you have just a constant voltage. You close the switch, and then eventually the capacitor begins to charge. Initially, if there's no charge across the plates, the voltage across the capacitor, call it VC as a function of time, initially the voltage is 0. And eventually it's going to reach some saturation value. And that saturation value is basically the voltage of that battery that we have. Okay, so this is kind of well known. The equation for the voltage across the capacitor as a function of time is given by something like this. You can look it up in any kind of physics textbook. Minus T over RC, and RC is that characteristic time constant for this DC circuit. Okay, so for the AC case now, what I want to do is I want to consider kind of two limits. I'm going to consider the low frequency case. So here I'm going to assume that the voltage as a function of time just looks like a square wave here that I've depicted over here. And the low frequency limit, it basically means that this time here, right, where the voltage is constant before I switch polarities, that whatever time this is kind of big compared to this characteristic time constant Tc. So let's just write that the time is kind of, the time t over here is big compared to Rc. In the high frequency limit, you can see I'm switching the voltage from this power supply kind of rapidly. So this amount of time here that we're just going to call t is actually small compared to RC. And RC is my characteristic time constant for this circuit. So we know now if I'm going to plot the voltage across the capacitor as a function of time, well, basically it's going to look like this curve over here, right? Especially if that, where I have constant voltage, if that's kind of long compared to this RC, it means that I'm almost reaching full saturation across that capacitor. And once I get to this point, well, now I switch. So that means the voltage across the capacitor is also going to switch. And I'm going to reach, again, maybe not make it all the way to saturation because I ended up switching, but it's going to look something like this. And I'm going to have this exponential growth here because I have a constant voltage for a certain amount of time. And this is simply going to repeat itself over and over again. Now, in the high frequency limit, well, again, you're just not going to get as high, right? Instead of reaching kind of this voltage all the way over here, because I'm not applying that constant voltage for a long period of time, I may actually only get kind of this high. So if you actually plot the voltage across the capacitor, well, for this first segment, I may only get here. Then for the next one, again, it's just going to repeat itself. But one thing that becomes clear, and again, I'm just doing something quickly and qualitative here just so we get a feel of what's going on. But because you're switching back and forth so fast, the voltage across the capacitor basically doesn't have enough time to reach the maximum voltage of the power supply. Okay, so we keep on getting, what we're going to get in this case here is lower amplitude as I increase the frequency. Right? If you compare the amplitude, the voltage across that capacitor, compared to the voltage being supplied by the power supply, the voltage across the capacitor ends up being much lower at higher frequencies than at low frequencies. Okay, so let's do some math now and actually work it out. write down Kirchhoff's loop rule for this circuit and see how we solve to actually find what is the current and what is the voltage across that capacitor. All right, so what I want to do here is I want to make this as simple as possible. So what I'm going to do first is assume that the voltage as a function of time of this power supply here simply has a very simple kind of time dependence, and it varies as cos of omega t. I'm not even going to put in a phase factor here, but it has some amplitude and it varies kind of just using the simple function. Now, one thing that you're going to get in AC, now the current that's going to flow here is going to be a current as a function of time. The current is not necessarily going to be in phase with the voltage. When you include a capacitor over here, it introduces a phase offset between the voltage and the current. So we're going to have to write the current a slightly different form than just the cos omega t. We're going to introduce a phase factor there. All right, before I do that, what I first now want to do is I want to apply Kirchhoff's loop rule to this circuit. So this is what the voltage varies as a function of time. I'm going to apply the loop rule starting at point A, and we're just going to go around in a clockwise fashion. Kirchhoff's voltage law simply says you add up all the potential differences across the different elements. You come back to where you start, you have to be equal to 0. So again, the first thing I encounter is the voltage across that power supply. Next thing I encounter is a resistor. There's a voltage drop across that resistor. We'll call it VR. And again, that's going to be a time-dependent function now. And there's also going to be a voltage drop across that capacitor, Vc of t. Again, I come back to where I started. This here equals to 0. Let's rearrange this equation here. So V of t, voltage from the power supply given by this equation 1 up here, has to be equal to the voltage across the resistor as a function of time, plus the voltage across the capacitor as a function of time. Right, and that, I mean, you could place any 2 points here. I could put points B and point C, and clearly you have to have this expression over here. Because regardless of how you go from point B to point C, you have to have the same voltage. Okay, so that's pretty straightforward. No hand waving there. So what we now want to do is let's put something in for my current as a function of time. First of all, it's going to have the same frequency. It's going to have an amplitude which I'm going to have to determine, which is going to be dependent on what value of the resistance I have and also the value of the capacitance. But the current as a function of time will probably look something like this. I max, some amplitude, and also some function that varies kind of sinusoidally like this. And here I also have to include a phase factor. So what I'm going to do now is I'm going to do some circuit analysis, because our goal here is really to find what both of those things are. That's the goal of all of this circuit analysis. If we can find what the maximum current is, we can find what that phase angle, I can then use that information to find the voltage across the resistor, VR of t, and also the voltage across the capacitor. So to find the voltage across the resistor, for that you simply have to use Ohm's law. And Ohm's law says it's the value of the resistance multiplied by the current flowing through that resistor. Well, that's what I'm calling I of t. The current is the same everywhere in this circuit. It's only a single loop. All right, so now if you actually substitute my expression here for I of t, the voltage across the resistor then simply looks like this. I max cos of omega t plus phi. Actually, you can see this phase factor now. Kind of important, right? It tells me that although I'm putting in a voltage which has no phase factor, there's going to be a phase difference between the voltage across the capacitor and the voltage of the power supply. They're not in lockstep with each other. So that's going to be important. And again, once I know I max, the value of the amplitude of the current, you can solve for what the time dependence of the voltage across the resistor looks like. Okay, for the voltage now across the capacitor, let's see how we can obtain an expression for that. All right, so our goal now is to find the expression for the voltage across the capacitor as a function of time, given that we've assumed that the current kind of looks like this. The first thing we have to remember is that the charge across the plates, or the charge on the plates rather, is proportional to the voltage. And if the voltage varies with time, then the charge varies with time. Now to link both of these equations together, what you end up doing is you simply differentiate the charge with respect to time, because that there equals to the current. That's the definition. So that there has to be equal to, by looking at my equation over here, that's the capacitance multiplied by, again, the derivative of the voltage across the capacitor with respect to time. Now this allows you to solve for what V of C might look like. Okay, because we know the left-hand side of this equation, it's just given by my expression up above. So what you can do is actually, you could say that the derivative of the voltage across the capacitor as a function of time is going to be equal to, bring the capacitance on the other side. So you have I max divided by the capacitance, and again multiplied by cos of the exact same angular term here. Okay, sorry about all the math, but it's required for this problem. All right, the next thing we have to do, again, our goal is to find VC. Here we know the derivative, but if the derivative gives me a cosine, right, you should know that VC then, if you integrate both sides, VC has to be equal to a sine. Right? If you integrate a cos, and what you end up doing, you got to be careful with that omega. You should get an expression that looks like this: I max omega c, and then you get sine of omega t plus the same angular term. You can double check that now. If you differentiate this with respect to time, you're going to see you're going to get the equation that's just above it. Okay, so now we have an expression for the voltage across the capacitor as a function of time. You see that nice thing about this equation over here is that it is still proportional to the maximum current here. Right? I mean, there's also this angular frequency term which appears in the denominator, and there's also the capacitance. However, if I'm just calling everything here in the front, let's just call this is going to be the amplitude. All right, this function over here is simply a function that varies between -1 and 1. So all of the amplitude basically comes from this term over here. So what we're going to do here is we're going to call this VC. That's just the amplitude, and then you have this time-dependent term over here. So VC is simply proportional to the maximum current, and let's put this omega c term that looks like this. Now what's often done here is, if we define the value that multiplies the current, just to write it in a form that looks like Ohm's law. If you remember, Ohm's law, at least for resistors, looks like this: a current times a resistance. If I want to write it for capacitance, kind of something similar to this, to Ohm's law, it's not a resistance here. What they call it is a reactance, and multiplied by the current. And from this expression over here, you can see that the reactance here of a capacitor is simply 1 over omega c. And this is what they call the reactance. Oops. One thing you could see that at high frequencies, right, the omega is going to be very big. So the reactance becomes very small at high frequencies. At low frequencies, when you divide by a small number, the reactance becomes very big. Okay, so just keep that in mind. Anyway, this is just going to be a definition, and it allows us to write at least the amplitude, right? There's still this important phase, but it allows us to write the amplitude of the voltage across this capacitor here in terms of something that looks like Ohm's law. So let's just quickly recap. So we had our voltage from the power supplied, which was simply given by the simple expression, didn't include the phase for that term. And it had some angular frequency, omega, and some amplitude, V0. I assume that the current now could be written in this form, and I left it the most general form possible. So it's going to have some amplitude, which I haven't found yet. We still have to do some work. It's going to have the same angular frequency, and it also has some phase factor here that we're going to have to solve for. Now we did a little bit of algebra in order to show that the voltage across the resistor is always proportional to the current, right? And the amplitude of the voltage across the resistor is given by VR, and that's given by my expression over here. It depends on the maximum current and times the resistor. The voltage across the capacitor, on the other hand, again, that one we had to do something a little bit different. And what it did was, it's not proportional to the current, it's proportional to, well, the derivative of the voltage across the capacitor is proportional to the current. So you have a cosine for here, you have a cosine for here, but we had a sinusoidal function. And remember, the difference between a sine and a cosine is a phase factor of 90 degrees. All right, we were able to write that the amplitude of the voltage across this capacitor, you can write it in a form that looks like Ohm's law. And what I mean by that is it depends on the maximum current, and the term that multiplies the maximum current is called the reactance, and for this case here it's simply given by this expression over here. All right, at the end of the day, what we have to do now with all of these expressions is all of these things have to be substituted into Kirchhoff's law, and they have to be used in order to solve what is the maximum current, what is that phase angle, and once you know those two terms, you can then go back and solve for the voltage across here and the voltage across the capacitor. All right, so let's go ahead and show you how to do that. What I'm first going to have to do, though, it's going to be easier. You notice that I have cosines everywhere. Cosine, cosine, except for the capacitor, right? However, like I said, those are connected to each other, right? If you remember from basic trigonometry, the sine of any angle is equal to the cosine of that same angle minus 90 degrees. Okay? So actually what I'm going to do is I'm going to write the voltage across the capacitor. I want to just have cosines everywhere. It's going to end up making my life a little bit easier. Okay. And all you have to do is simply, the amplitude doesn't change. All you're doing is rewriting this as cos of omega t plus the same angle phi, and now it's going to be minus 90 degrees. The reason I want it in this form over here with a cosine is now you can automatically see that there is a phase difference between the voltage across the resistor and the voltage across the capacitor. And that phase difference is basically 90 degrees. Okay? So what we now have to do is we have to substitute everything back into Kirchhoff's voltage law and do a little bit of math to see how we can calculate the phase angle and the amplitude of that current. All right, so what we want to do now is, again, we want to start solving things now. So we want to solve for what the angle phi is that appears in some of these terms, and we also want to find what the maximum current is, which appears in here, and then that will enable us to solve for these amplitudes. Now, again, everything comes down to solving Kirchhoff's loop rule over here, which led us to this expression over here. If you go ahead and substitute the voltages in this equation here in the green box, you get the expression down here in the lower right-hand corner. Now we have to solve this equation for phi and also for I max, which appears in both of those terms. That's actually pretty hard to do. You could use some trigonometric identities to kind of break these terms up. You'll do a little bit of math. There's an easier way to do it, and that's using Phasor. So I'll show you how to do that quickly. This video is not on Phasor, so I'm going to go rather quickly on this. But what we're going to do, let's start with V of t and show you how to represent that in this in a Phasor diagram. First of all, although it's a scalar, we're going to represent it as a vector. The magnitude of the vector is defined by the amplitude. And where we draw it in the plane, we're going to define the zero angle to be right along this x-axis. So that means if I'm drawing it like this, that's because I'm at some angle omega t. Now at some later time, that vector is going to be over here. It's going to have the same magnitude. Right? At some later time, the t gets bigger, so omega t would be, let's call it omega t2, might be over here, and it's still the same amplitude. Okay, so you can decide to plot this vector anywhere you want. It really doesn't matter. Okay. The simplest way, however, since we're going to really have to draw all three of these vectors here, I'm going to show you a little trick. And what I suggest doing is starting with the resistive one. And since we're able to plot it anywhere in the plane, we're going to plot it right here. So we're going to plot the resistive part, the voltage across the resistor right here, and that there has an amplitude VR. So that means that this entire angle, again, the angle is defined from this x-axis, this entire angle here, although it's 360 degrees, again, this would represent the angle omega t plus phi. So now if I want to go ahead and plot V0 now, if I call this omega t plus phi, that would mean that V0 should be somewhere over here in this fourth quadrant over here. And it's going to be plotted something like this. This here would be V0. And you see that this angle over here is phi. So I kind of have to take away phi, right, from the red one. All right. And the reason I do this now is because once you plot the voltage across the capacitor, look at the angle for the voltage across the capacitor. It's the angle of the red one, right, omega t plus phi, except now I have to take away 90 degrees. And if you take away 90 degrees, the amplitude has to be along this axis over here. And again, the amplitude is going to be Vc. That's the amplitude of this term. So now actually you see that my equation in the green box, this is what you want. You want V0. And again, it doesn't matter where you plot all of these things. They're all going to rotate together at the same rate omega because they all have the same angular frequency. So irrespective of where you plot this, you're always going to have a picture that looks like this. Okay, VR is going to be a little bit ahead. VC is going to be lagging VR by 90 degrees, right? That's going to be the angle between both of those vectors. And V0 is going to lie somewhere in between VR and VC. All right, so now in order to kind of link these up, now you can see that VR is simply the x component of the vector V0. And VC is, although it's along the negative y-axis here, is simply the vertical component of that vector. So we can simply use Pythagorean now to link all of those up, and you get V0 squared must be equal to VR squared plus VC squared. Now if you remember the expressions for the amplitudes, right? The magnitude of VR was written as the resistance multiplied by that maximum current. And then I square everything. And the way we had written the amplitude of the voltage across the capacitor, that was using the reactance. And again, it was still multiplied by the same current. All right, and all that equals to V0 squared. You see I have I max in both terms. You can factor that out. So this here becomes R squared plus X squared. Open a bracket and everything gets multiplied by I max squared. All right, now what you can do is simply take the square root of both sides. Our goal here is to solve what I max is. So I have an equation here that really has no angle phi in it, which is kind of nice. So that really allows me to find what this current is. So if you take the square root on both sides, that'll eliminate this. You're going to be left with the square root of everything here. So this is resistance squared plus reactance squared multiplied by that maximum current. This we often write in terms of, we just group together everything under the square root. This is what's called the impedance. In an AC circuit, okay, the impedance has a resistive term and a reactive term. And we call that the letter Z. Okay, so we call that all of that Z. So that means we still have to have this maximum current over here. All right, so the last thing I'll do is simply solve. So my maximum current is going to be whatever driving voltage I decide divided by the impedance, Z. Let me go ahead and box this one up too. This is going to be an important equation. Now there's one more thing that comes out of this equation here about using the Phasor diagram, which is kind of nice. You can easily write down an expression for the angle phi. Right? Since I know both of these components, or I know the hypotenuse, you can use any of the trigonometry, right? Sine, cos, or tangent. Let me use tangent, it's probably the easiest one. So tangent of the angle phi is going to be equal to VR. Again, it's sine over cos. Sine of the angle phi divided by cos of the angle phi. All right, and sine, if you're, I'd be a little bit more careful here. This should be the voltage across the capacitor. And let me put a negative since it is kind of below the axis over here. And divided by the voltage across the resistor. Now, just like we did before, we can write these in terms of the reactance and the resistance. And what you end up getting is that the maximum current will cancel out of both of those terms. And you're simply left with the reactance divided by the overall resistance over here. So that simply allows me to solve for what the angle phi is for a RC circuit. So let's go ahead and write that out. So inverse tan of minus x divided by the resistance. Okay, let's also include that one in the green box. And this is how you can solve very, very simply for the maximum current and for that phase angle here, which gets plugged into all of these expressions. All right, now I want to go in and go look a little bit more closely now at the voltage across the capacitor, which was the overall goal of this video. All right, so now let's go back to our circuit. We want to look at what's going on. What does the amplitude look like here of the voltage? We know it should get smaller. Let's make sure everything kind of comes out that way, right, from our qualitative look at what was going on here. So here's my expression for the amplitude. Again, I'm not too worried about the phase angle now because I'm really just interested in the amplitude. So let's go ahead. Amplitude is written as the reactance multiplied by that maximum current. And the value of the reactance is 1 over omega c. And the maximum current is what we just solved for. So you have 1 over omega c, and that maximum current was the driving voltage, V0, and divided by that impedance, by the impedance Z. We can go ahead and substitute that in. Omega c, V0, divided by, again, here we have the square root of the resistance squared, and plus the reactance squared. The reactance, again, I'm just going to go ahead and just substitute what the value is. It's 1 over omega c, and you have to square this entire thing. Now, what's the best thing to do at this point is actually to bring in the omega c that's on the outside of the square root. I recommend kind of bringing it into the square root, and if you do that, you have to square everything, right? So, and what that is going to do is it's going to kind of simplify the second term. So let's go ahead and just do a little bit more math here. Vc, let me bring the V0 on the other side. So this will be the amplitude across the capacitor with respect to my driving voltage amplitude. This is simply going to be 1. If I bring in the omega c, and again, this second term here is simply going to end up being 1. So actually what I'm going to do is I'm just going to write it as that. 1 plus... again, now you're still going to have this resistance squared, and that is going to look like this. Omega squared, once I bring this guy inside the square root, and everything else ends up being resistance squared and capacitor squared. And what I really like about this form here is that you can see that this RC, which is the same RC time constant that we had previously, ends up coming back, even in the AC case, as an important parameter. This here has units of time, and the omega has units of 1 over time, right, or radians per second. So that works out. So this is a dimensionless number, and everything here should be dimensionless since we have a voltage over another voltage. So now what you end up doing is it's important to look at some limits here. So let's look at low frequency, okay? And now you actually know it's low frequency with respect to what, right? It's when, so low F, or low omega, if you want to call it that. Again, those are proportional to each other, so it's not that big a deal. And its omega is small with respect to 1 over RC. Okay, in this limit over here, basically you could just neglect this second term, right? If omega is kind of small, it's approaching 0, for example, then forget about this. You have 0 multiplied by RC. Don't have to worry about that term. So what you're left with here is that the voltage across the capacitor divided by V0 is simply approximately going to be equal to 1. And that's cool, right? That means that the voltage across the capacitor is basically essentially just the same amplitude as the voltage that you're driving it. And that's exactly what we would expect. Right? If you switch this very, very slowly, you'd expect to always reach that saturation point. All right, what about in the high frequency limit? High frequency. So that's the opposite limit now. So our omega is going to be very big, right? So in the high frequency limit, what you would end up doing, again, we're looking at the ratio of the voltage across the capacitor with respect to that driving voltage. In that high frequency limit, basically what you could do is you could forget about this number 1 here, right? And high frequency would be omega is much, much bigger than this 1 over RC. All right, so we don't even have to worry about this number 1 here. That's not going to add a lot to our solution, right? If this term is so big compared to the 1, then you just forget about it. And that means that you could take the square root now of this entire term, and you're left with 1 over omega multiplied by RC. Okay, so that's the solution here, kind of in the high frequency limit. And in the really high frequency limit, you can see that it basically will tend to 0. Okay, so we have this limit. So that means that the voltage across the capacitor will basically be 0 in the very high frequency limit. All right, what we can now do is ask ourselves, well, for which frequency now is kind of the power, the rate at which energy is being stored in that capacitor, half of the energy that you're putting into the circuit. All right, so in this case here, really what we'd be interested in here is we want to kind of square both sides. And what we would want now is this factor to be equal to a half, right? For which frequency would this here be equal to half? So the first thing you do is you got to square both sides. That's kind of nice because this eliminates that square root. And how do you get that? Well, you'll get that, you'll get this denominator here equal to 2 if, right, that's all we need. We want 2 equals to 1 plus omega squared and RC squared. All right, so you're left with omega squared should be equal to 1 over RC. Everything's squared. So at the end, when the frequency equals to 1 over RC, you're going to get half the power. All right. If you take 10 log of this term over here, right? So 10 log of VC over V naught squared, when that term equals to 1/2, again, you do the same thing, 10 log of a half. A log of a half is minus 0.3. So this is actually what you call a 3 dB drop. Right? So you get 10 multiplied by 0.3, or negative 0.3 rather. And you get that 3 dB drop. Right? You get half the power stored in that capacitor. All right, so now let's go ahead and sketch what this looks like now. Since we know the low limit, we know the high limit, and now we know when the power drops off by 3 dB. All right, so let's go ahead and sketch that now. All right, so the way this looks like now, if I plot as a function of omega, and I'm plotting again, I'll just plot it on the logarithmic scale over here. At low frequency, we have 0 dB, right? Because we have VC over V naught was equal to 1. So if I square it, it's also equal to 1, and that means log of 1 is equal to 0 dB. And what you had now, it ends up being pretty flat, and then it starts to roll off. And then it also kind of has a straight kind of linear behavior if you plot things on a logarithmic scale. Now, one important point that we just solved for was when we're actually 3 dB below where we started. All right, so we're minus 3 dB, and we said we got that when our frequency, omega, was equal to 1 over RC. All right, so this is what they kind of call the knee of this curve over here. So again, this is our low-pass filter, really, right? Because at low frequencies, all of the amplitude gets through. And once you get at high frequencies, basically above this cutoff over here, then you start rolling off quite rapidly. Actually, the other thing you can ask yourself is, what is the behavior of this section, right? It goes down, right? But how much do you lose, for example, every time you double the frequency? All right, so we can have a look at that now. All right, so now our question is, we really want to know, what is this roll-off here? So what is a roll-off in high frequency limit? It certainly drops, but on this dB scale, how many dBs do we get, for example, every time I double the frequency? All right, so let's double that frequency. So here's omega. What if I go over here to 2 times omega? Okay. And again, we're really looking at the high frequency limit, so we can really forget about this number 1 here. So let's consider this is our power at this frequency, and let's look at the power, for example, when I double the frequency. The power 1 plus, if you double the frequency, you get a factor of 4 there. RC squared. Okay, and this will be kind of power 2, right? And power 1 is kind of this one over here. All right, so power 2 should be lower. Let's figure out how much lower. So let's take the difference between both of those. All right, so you get P2 minus P1. And again, in the high frequency limit, right? In the high frequency limit, we can forget about that number 1. So P2 is simply going to be 10, a natural log of 1 divided by roughly 4 omega squared RC squared. And again, minus 10, a log of omega squared RC squared. Getting a little bit crowded over there. We'll make some more room down over here. Again, we take the difference here between two logs. It means you divide them, right? So we're going to have 10, a natural log of, again, all of these terms are going to cancel out. If you take the division over here, you get RC squared like this. And here you get 4 omega squared in the exact same term, RC squared like that. Let's cancel out what's common. All right, so all of this to say that 10 log of 1/4. A log of 1/4 I don't know, but I do know log of a half. All right, so this will be 10 log of 1/2 multiplied by 1/2. 10 log of 1/2 plus log of 1/2, using some of the properties of logarithms here. And the nice thing about this one, log of 1/2 is minus 0.3. So I'm going to go back on this side, so you get 10 minus 0.3, and again minus 0.3. I could have done that in the calculator, I guess. That'll give me minus 6 dB, and what we call this is an octave every time you double that frequency. So that is really what the roll-off is here. That's kind of the slope of this line. Drops off every time you double the frequency. You end up being 6 dB lower in power. Okay, so I think that's kind of it for this problem over there. This is an example of a low-pass filter. The amplitude only drops off once you go to high frequency, and it drops off, at least in terms of the power, is 6 dB per octave. All right, folks, if you have any questions, don't be shy. Just leave a comment. Hopefully I could try to explain it to you.